or something like that.
All right, it's time for us to get started.
Okay.
Reminders, we have an exam on Friday. Study guide is posted. My plan at the moment is to go over some practice problems with you all tomorrow. The subjects for those were the context-free pumping lemma, and I have had a request for just Turing machines in general, in addition to the more specific request of non-deterministic Turing machines. So I will come up with associated problems. Are there any other sections of the study guide that people feel like they could use some extra practice with? Accountable versus unaccountable. I will add that to the list.
Just like an example of a show.
Yeah, okay. Let's see, we will expect something like a homework assignment to be released tomorrow-ish. I'm open to pushing that to later next week than Wednesday, since there won't be a new assignment to be pushed at that point, so I will probably make that due either Friday or Monday. Next Friday or the following Monday, the very last couple of days of class. And then I'm also going to get the last project to you as soon as I reasonably can, so that you have as much time as possible to work on that.
For this last homework, will we be expecting it to be graded for the final?
Probably not. I know that's,
If we were, then I'd probably say. We'd probably. Hey, but
yeah, I honestly don't know at this point. Grader is farther and farther behind, further and further behind, it's not a distance. So we'll see.
I know that's a future problem.
Yeah, that's a great point, and I would like to make sure that it gets back to you. But as usual, if for some reason it is not returned to you ahead of the exam, my office hours are open to go over any of those problems, expectations for those problems, your solutions to those problems. So make sure that you make use of those. I know that we've seen quite a few people in office hours, which is excellent. I love to see the engagement. But it may be necessary just to make sure that you get the feedback that you need ahead of the final.
Monday before the final, are you going to have regular office hours or extended office hours or, because we don't have class?
Do we not have class that
I don't
Monday?
think
I
so.
don't,
We have class.
I think
Oh, we do?
we technically have class.
It's a weird recorder.
Yeah, so
We have class Monday and final start Tuesday.
That's dumb. I
It is
thought we didn't have that.
So, yeah, my plan is to have Monday be 100% a review day, so people can bring their questions. We'll just go over whatever questions you have. I'll spend that however it would make the most sense, be the most use to you ahead of the, and I think we have our final like the very first day, 8 AM on Tuesday. Great.
So.
Yeah.
Here at ATC. Mondays. Yeah. That's the first time.
No, not this upcoming Monday.
Oh, okay.
Next Monday. Yeah.
Yes.
Yeah. So we will dedicate that to be 100% a review day. And we'll see. I assume that projects will be pushed, since we do have that class on Monday, projects can be pushed to that Monday as well. So both the CYK algorithm and this upcoming project, because I want to give you enough time to implement this upcoming project.
Still trying to take the input.
Questions about the upcoming schedule? I don't know, I want to say wind down our quarter, but it's not winding down, it's winding up. There's a lot happening at the end of the quarter.
Yeah.
Questions or concerns about the schedule? We'll do what we can to make sure that people have what they need, given our limited time and resources. All right, last time we introduced this concept of a first function. What was the purpose of the first function? What is it doing? Yeah,
For the lack of better words or term, it's just trying to grab like the first thing in the production, I think, and then try and chain them together.
yeah, so we have some production. And we're very curious about, given that we're expanding this non-terminal, what are all of the possible first terminal symbols that could appear in a string from that point? So the first of a terminal is defined to be itself. The first of a non-terminal is the set of all possible terminals that could be the first symbol of a substring that's derived from that non-terminal. And this becomes very useful for selecting relevant productions when we're doing a search, because we don't want to select a production that can't possibly start with the terminal that we're looking for in our substring. If we want to generate a particular substring, we don't want to choose something that can't do that. So it's worth going through the work to be able to eliminate possible productions from our search tree. We're basically trimming the tree. We're cutting off massive branches of search space as we figure this out. Ring a bell?
Yeah.
We went through a first example of this with a grammar without lambda in it. And we decided that, all right, first of S started out being, we say it's the first of itself, union the first of every possible production that could come from it. So S arrow ASB and S arrow A are all productions. So we need the first of S union the first of ASB union the first of A. The first of S is currently empty. This may be added to in the future. Union, the first of ASB, is just the first of the first character of that. So the first character of ASB is the terminal A. So we union that in. And then the first of A, and we have no way without asking a further question to understand what the first of A is. So we need to kind of recursively go figure out what first of A is. So first of A is itself, which starts out empty, union, the first of B capital A, union the first of C, and first of B capital A is just again that first symbol in there since it's a terminal. So we grab the B. First of C is just C, since a first of a terminal is itself. So union all those together, we get BC. We can now back substitute that into first of A. And we get that first of S is A union BC, which gives us the set ABC. And that tells us that starting at the start production, there can be strings that start with any of the three possible terminals, A, B, and C, via some production path. And that turns out to be very useful information as we attempt to parse. Questions on this example before we move on? It becomes harder when we introduce things like this. Maybe. Let's find out. Take your best stab. There's only one non-terminal here, so we only have to figure out what first of S is. So spend a couple minutes, talk to your neighbors, and see if you can figure out what this does. Intuitively, what should the answer be? B. Is there any way to start this string with an A? No. So let's see if we can go back and follow this process. Everyone have the grammar written down. I can go back to the pseudocode. There we go. So we want to algorithmically derive that the first of S in that grammar is just B. You think we got there? So we start by defining first of S as first of itself, union first of SA, union first of B. First of B is just itself. Now we can say first of S is first of S, union first of A, union first of B, which is first of S, union first of S, union B. And this just continues, right? You just define, you have more copies of first of S, first of S, first of S. As soon as you see that loop, you can terminate.
I think I missed. Why did first of SA turn into first of S?
Because it's the first character in SA.
Okay.
We only have to worry really about looking at the second possible letter there if there's a production that takes that S and turns it into a lambda.
Okay.
So we are going to see that grammars with lambda make life just a bit more complicated. So we need the extra rule that first of lambda is lambda. Also, if first of some non-terminal can derive lambda, we also have to consider what happens with the next symbol in the production. So this means that if the second symbol can also derive lambda, we have to consider the third symbol. If the third symbol can derive lambda, we also have to consider the fourth symbol. So we're just going to continue to iterate until we find a production that does not lead to lambda, or we reach the end of our production. So let's get an example of a first function with lambda. Here's our grammar. A bit more complicated. As usual, we're going to begin with first of S is the empty set, first of A is the empty set, and first of B is the empty set. Until we get more information, we're just going to define them initially as empty set. So we see that first of S kind of depends on first of B. First of B doesn't really define or depend on anything. We get B or we get lambda. But since we can derive lambda from B, we also need to consider for first of S this A, because it very well could be that this S goes to B goes to lambda. So the first character of this string could be defined by this A. Does that make sense? So we were doing some kind of derivation of this, and we said, S arrow B, A, D arrow, we're gonna define this B to be this lambda. Then we're able to do straight AD, which means we're able to define this A as either C capital A or D. So we have CAD or DD. And you see now that the definition of what starts this string actually came from this capital A and not from this B, because we can derive lambda from B. So we need to consider that whenever we have lambda in our grammar. So with all of that in mind, go ahead and take a stab at this. See if you can define the first function for all non-terminals in this grammar. Is there a non-terminal that makes sense to start with here? We don't have to start with first of S. We could start with any non-terminal and attempt to grab that definition. What non-terminal would you start with?
A.
A, that seems like a reasonable choice. Because every possible production, A arrow something, starts with a terminal. So it's not going to depend on the first of any other non-terminal. I think that's smart. Yeah, too much. Think we got it figured out? All right, first of A and first of B are mostly straightforward. First of A, we see that there are two productions that lead to terminals, C and D. So we are going to make sure that that is our first of A. First of B can either derive B or lambda, and we said that first of lambda is lambda, so we need to make sure that it stays in that set. First of S is now going to start out being first of S union first of A, capital S, C, first of capital B, capital A, D. We can see that first of something that starts with a terminal is the first terminal in that. Calculating first of BAD is going to be a little bit more difficult. So we know that first of B is B and lambda. So we add B to first of capital B, capital AD. But since we know that B can derive lambda, we must also consider first of A. This is why we add lambda to first of B. Because when we attempt to grab what is first of B from first of S, we see that lambda, which tells us we also need to consider the next character in that production. So we must also union it with the first of A. Since first of A is CD, we add that to the element to the set of first of capital B, capital AD, which means that first of capital B, capital AD is all of BCD. We union that with the first of A, capital SC. And we get ABCD. Note that the lambda went away. It just tells us to also consider the next element. Does this make intuitive sense? That starting with the start non-terminal, we can derive strings that start with A, B, C, or D? So this isn't too bad. It seems fairly algorithmic, like it wouldn't be too bad to implement. This will be the first part of the second possible project in the class, is to implement, given a grammar in a file, parse that grammar and produce the first function output. One thing we may also want to do algorithmically rather than intuitively is to be able to define whether or not our first function is correct. So if we go through this algorithmic process, come up with a set for the first function, we want to be able to work in the opposite direction and show that we can derive at least one string that starts with every element of the first function set. So for each element of first of S in the grammar, on the last slide, we want to show a derivation where some terminal, that terminal begins some string. So we can use the production S, A, capital SC, that shows that we've been able to derive a string that starts with A. S arrow capital B, capital AD, arrow B, capital B, D, capital A, D, shows a derivation where B comes up first. S to capital B, capital AD, to capital AD, to C, capital AD, shows a derivation where C begins the string. And finally, the last one shows D. This tells us that first of S is correct, but we also need to do the same thing for first of A. Since that set was CD, we want to show that starting with the A non-terminal, we can produce strings that start with C or start with D. And then for each element of first B, we also want to derive a string that starts with B and an empty string. So we have the associated productions to be able to string them together and be able to produce strings that start with those characters. So this is the opposite direction of working given a first function or given the complete first function, showing that your first function is correct. Questions about the first function? All right, it's time for the slightly more difficult one, the follow function. So what do we think follow means? If first means that we care about the set of terminals that could appear first after a non-terminal, what is follow going to mean?
The set of terminals that come after.
Yeah, it's going to be after that non-terminal at some production at some points right-hand side. To say, given that we have something like a capital A somewhere, what could follow from that? Why do we care about this? We again need the knowledge of this to figure out which production to expand based on the sequence of terminals that follow from the string that we're trying to derive. Or in this case, the program that we're trying to derive. To do this, we need to add one more symbol to our toolbox, so we're going to use $sign. $sign is going to indicate the end of a string. So we just throw it at the end of a string to show we're at the end of a string, which becomes necessary as we figure out follow. As you do this, you can start including it in any follow functions definition to indicate that that particular non-terminal could show up at the end of a string. So the first step of follow is to add $ to follow s. And just like before, we're going to have a set for each possible non-terminal in the grammar. So follow of s always contains $. As the next thing I'm going to show you is the pseudocode. Note that V and W can be any terminal or non-terminal. That was described or defined in the book, but not in the part of the algorithm that I grabbed. So V and W can be any string of terminals and non-terminals. I think it's just a single terminal or non-terminal. So we add $ to follow of s. For every non-terminal that has a arrow, some terminal or non-terminal, followed by a b, then follow of a is in follow of b. So we have a left-hand side with an a, arrow, some terminal or non-terminal, followed by capital B, some other non-terminal. This tells us that everything in follow of A is in follow of B. That's only if the B ends the string there. If there is a B in between some terminal or non-terminal and another terminal or non-terminal, then we have to follow this process. We take the first, so we're going to call the first function, this is not the follow function, we're calling the first function on that last character, either a terminal or non-terminal W, take out lambda if lambda is present in that, and add all of that to follow of B. If lambda was in first of W, then everything in follow of A is also in follow of B. So it's actually simpler algorithmically, but we need to understand the first function because it is a subroutine potentially of the follow function. And again, this is just stepping through the actual process. I think this will become clearer as we do some examples. Questions about anything on the slide before we dive into our examples? All right, so here's a grammar. Same grammar as our first example before. We want to calculate the follow function for each non-terminal. There are only 2 of them. Our first step again was to add $ to follow of s. So now we note that s appears on the right-hand side of a capital SB. So we go back and we look at the things that follow s. So we add b to follow of s because it follows s. This redefines follow of s to be $B. Since A appears on the right-hand side of A and B capital AA, we have the latter, we add A to follow, that should be a capital A, sorry, not a lowercase a, follow capital A. I'm just going to make that change now because that's going to be confusing. For the former, we want to say that anything that follows S can also follow A. that make sense as to why?
I'm not sure why that would be.
Because this S can derive the A immediately. So whatever follow, if we do this and then define this S to be A, whatever follows S can also follow A when we do that substitution of S for A.
I actually didn't notice that production, I just didn't see it,
Gotcha.
so that's why.
So we can now define follow of A to be everything in follow of S plus this A. I guess union this A to be correct. So we have A, B, $sign. So this is the simplest possible follow scenario because we didn't have to call first of anything. There are no lambdas. There's nothing super tricky about the function, about the grammar. It's just steps through the logic of calculating the follow. Another example. We're gonna do our last example with our lambda in the grammar. So the steps we're gonna walk through. As usual, we add dollar to follow of S. Saying that this S can derive the entire string, right? So we need to add dollar to the end of that. So to calculate follow of S, we need to figure out, all right, what are the non-terminals that adhere to those requirements in the algorithm? So we notice that S appears on the right-hand side of A, capital S, C. So since S appears on the right-hand side there, we add the following character to its follow. Since C follows the capital S, we add C to follow of S. We'll calculate follow of A. Where can A be found on the right-hand side of things? There are three of them. Both productions, S arrow something has an A arrow C capital A. So we'll start with A capital S C. When we see that there's a non-terminal on the right-hand side of that, we need to recursively call first of that string after the A. So wherever that A happens to be, calculate first of the remaining string. So what's left over from the right-hand side of A after we reach A in that right-hand side is capital SC. We calculate the first of that, and we add everything from that to follow of A. First of SC is ABCD. By following our logic of first. We saw this before when we calculated this. We also see that A is on the right-hand side of capital B, capital AD. Since there's a symbol to the right of it, we need to calculate the first of it. First of D is D, so we add it to follow of A. It's already there, there's no additional change. A is the right-hand side of C capital A. Since it's at the end of the right-hand side, we add everything from follow of A to follow of A. How would we calculate follow of B? What do we think is there? Go ahead and take a couple minutes, talk to your neighbor and see if you can calculate follow of B, given all of the information that's here. What's going to be in that set?
So I'm a little lost. I'm trying to figure out So what is the right-hand side of these productions? Like when you say the right-hand side of AASC, what is that?
Gotcha. Yeah, I guess I've been using right hand side to mean a couple different things. So here's the right hand side of the production, but here's the location of the capital A in that. So we want to grab everything to the right of this, right of that capital A on the right hand side,
Okay,
and calculate first of that substring. So follow is always looking for, if we're defining follow of A, we're gonna look for A's in the right hand side. And then we're gonna say what follows that.
so would the right-hand side of S be C, for example?
Yeah. So we're calculating follow of S. We see that S appears here, what follows S is C, first of C is itself.
Okay,
And that's the only place that S appears, so follow of S is just C and the dollar that we have in the first step. So B appears in two places. Here and here. Have an answer? What do we get?
For what follow B,
Yeah,
C and D,
C and D. How do you get there?
it would be first of AD and first of D, because that's where the B's are.
Yep,
And then first of AD is just first of A, which is C and D. And then first of D is just D, which doesn't change it.
yeah. So. Follow of B. B appears on the right-hand side of two things. So first of AD is CD, exactly as Hunter said. It's also on the right-hand side of B capital BD. So we add D there, but it's already there. So we don't double count it. It's a set. So it is just CD. Just like with the first function, we can go through the reverse logic to attempt to show that our follow function is correct. So for every terminal that we have in our follow function, for each non-terminal, we want to derive a string that shows that that terminal can immediately follow that non-terminal. So we'll use the same grammar, and here's the associated logic. We can show that follow of S is C $sign. So we want to basically, we know that dollar always follows the start symbol. Since the start symbol can derive the entire string for every possible string, we start with the start non-terminal. So we don't need to justify that. It's just there by definition. But C is there. So we want to show some derivation where C immediately follows a capital S. So here's where we do it. It happens immediately. Follow of A is A, B, C, D. So we need to say immediately following the non-terminal A somewhere in the middle of a derivation. We need the character A. So if we do the first line of this, we get S, A, capital S, C, and we see as we derive this, we then get this substring where the A follows the capital A. And then here we have, as we derive this, we have a B following a capital A. And a B derivation. Here we have a C following a capital A. And here we have a D following a capital A. So you just need to find the associated derivations where in the middle of that derivation, you have a non-terminal. That represents the non-terminal that you're trying to do for each element of the set, show that you can have that terminal immediately following that non-terminal. For follow B, you just have these associated derivations. We want to show that we can get a C or a D immediately following a capital D. Using this derivation, we get the C immediately following the capital D, and here we get the D immediately following the capital B. So do note that this justifies the inclusion of each of these. It doesn't show that there shouldn't be more things in the set. Right? There's nothing that says that there's no possible derivation of capital B that follows with a lowercase b. So this justification doesn't fully show it's correct. It just shows that everything that you added to this set can be rederived to follow that non-terminal. Questions on the follow function? It's not too bad once you understand what it does. All right, probably our second to last topic in here, we're gonna start talking about LL parsing. And LL parsing will use both the first and follow functions as part of it. So now that we have an understanding of these algorithmic subroutines, we can apply them to trying to find an efficient way to parse a grammar from the top-down approach. We talked about top-down versus bottom-up. LL is a top-down approach, LR is a bottom-up approach. There is one additional preliminary to LL grammars, and that is that we need to have some intuitive way to convert a context-free grammar into a non-deterministic pushdown automata. If we can think about the actual process of how this conversion happens, that's exactly how the LL parsing algorithm works as well. So the work that you have to go through to convert a grammar into a non-deterministic pushdown automata, same thing. That's exactly how the LL parsing algorithm works. So let's talk about this at an intuitive level. So how do we convert a context-free grammar into a non-deterministic pushdown automata? What we found throughout most of this class is non-deterministic pushdown automata have very few states. Very, very, very few states. And there's one big parsing state. So we can model a context-free grammar with a non-deterministic pushdown automata whenever we see a non-terminal. We can pop that non-terminal off the stack and replace it by the sequence of tokens that is the definition of that production. So a left-hand side is a pop and a right-hand side is a push. We're replacing the definition of a non-terminal with its production definition. So we're going to simulate the context-free grammar via a pushdown automata. We start with our initial state. The entire purpose of this initial state is just to push the start non-terminal onto the stack. So now instead of having arbitrary stack symbols, these are going to be stack symbols that represent non-terminals, variables. Whenever we pop a non-terminal, we're going to replace it with a definition of some sequence of symbols that that non-terminal could represent. The state Q1 is going to be the state where all of the parsing happens. We're going to be doing all of this replacement and calculation in Q1, and then we'll transition to the final state on an empty stack. So Q0 to Q1 pushes S onto the stack. We mentioned that already. Here's the transition definition. From Q0, without reading any input, with a bottom of stack symbol Z, we're going to move to state Q1 and push S onto the stack. If we want to define what Q1 does. For each production, we need to have a rule associated with replacing a left-hand side of the production with the associated right-hand side. So the general rule for this, for every production rule, some non-terminal arrows, some sequence of symbols, these can be either terminals or non-terminals. We want to add an associated transition to our NPDA that says we're going to be going from state Q1 to state Q1 because we're not changing states. We're not reading any input, so we want to be able to say, by popping A off the stack, we're going to replace it with this entire list of symbols. Right, that's kind of how we have a definition of A. Think of it as a variable. We're defining A in terms of this sequence of symbols, either terminals or non-terminals. We can make this substitution and say that they are equivalent. This variable A represents this sequence of data. So we're going to just make a replacement rule that says replace the A on the stack with this sequence. Some of those will be terminals, some of those might be non-terminals. Now, all we need to do is make sure that the symbols that we see on the input string get matched as we do this stack operation. So the order they appear in the stack. So for every terminal symbol, we want to be able to pop the terminal symbol and read it in the string. Does that make sense? If the top stack symbol is a terminal symbol, that says that we can read that symbol in the input string. If it's a non-terminal, that non-terminal can't appear in the input string, so we replace it by its definition. So when we get transition from Q1 to Q1, we're going to pop the terminal and read it from the input. So we're going to read a T in the input, pop a T from the stack, and push nothing to the stack. So it gets rid of the terminal, and it reads it from the input string. Does that concept make sense? Some blank stares. We will have an example with this. We also know that the transition to the final state Q2 can only happen if the input has no more characters left and the stack is empty. The same rules that we've always had with our NPDA. So we add that to our list of transitions. All right, let's very quickly see what this could look like. So we have a simple grammar. I'm probably going to go over this too fast because we have 1 minute left. But we'll come back to this in a lot more detail next time. We start at Q0, we push S onto the stack, we transition to our parsing state. So there's the transition. We add a transition rule for each possible production. So we need to be able to replace S with ASB and replace S with A. We need to be able to replace A with B capital AA. We need to be able to replace capital A with lowercase c. So those are the associated transition rules. We're just looking at every possible definition of our non-terminals. Then we need transition rules to shift our input symbols onto the stack. So we basically, this is the popping of the terminals when we read them in the string. So if the top of the stack is a terminal and not a non-terminal, we want to read it from the string. Then we just add the final state transition. And that's it. We converted this grammar into an NPDA that looks like that. I will be walking through this with an example string as the next thing that we do. So we can actually see how the stack manipulates. So we can actually see how it reads the string and why this construction is correct. And we'll do that not tomorrow because we're doing practice problems, but we'll do that on Thursday. See you tomorrow.